This video is intended to be a mild demonstration and instructional video intended to help you understand how to operate my latest circuit simulation, because these are, generally speaking, crude prototype or proof of concept, actually, simulations that require a certain amount of involvement on the part of the observer in order to know how to operate them. Usually there are switches to close and values to change, and the simulator has to be stopped and restarted, and so it sometimes can be a little complicated to know how to run these things instead of just letting it do everything for you, because these are not simple circuits by any means. And to add to that caveat, free energy would not be easy if it were not for the fact that if it were easy, Mother Nature would blow up. And she can't let that happen. Electricity by its nature is a wild stallion, or a wildfire, a wild forest fire that gets out of control, in that it wants to do what it wants to do, when it wants to do it, however it wants to do it, to whatever degree. And it never asks for anybody's advice or guidance, counsel, or permission, most importantly. We have learned in the electrical engineering field to suppress and literally tie a tight noose around electricity to suppress surges and to control it with an iron grip. And most of the time we succeed. Sometimes we don't. Sometimes anomalously it gets out of hand and things go awry, namely things blow up. Well, I try to encourage that in order to learn how to regulate it from the start, so that I don't wait around for something to happen and then, okay, now what do I do? Try to shut it down. Oops, you shut it down. It just explodes even faster, or escalates towards an explosion even faster. So it's a really peculiar thing in which not only is it a wild stallion, but another analogy applies, and that is through the looking glass. Alice in Wonderland, through the looking glass. Lewis Carroll's peep into a reality in which things are not as they seem, not as we are accustomed to. And that's literally the world and the realm of surge-oriented circuitry. For instance, in this circuit you see in front of you, there are switches. There are 4 of them, and they're regulated by a clock. Now, in this particular circuit, not in my others, but in this one, the clock speed regulates the toggling of the switches, which in turn regulates the growth rate, because this is not a very powerful circuit, and that's a good thing, because powerful circuits tend to get out of hand. And I believe this is one of the pinnacles of success that Tesla had with his special generator, because that's what this circuit is meant to loosely simulate, not accurately, but loosely, close enough, was that it does not allow the surge to get out of hand. In fact, you gotta pump it, and you pump it by toggling the switches, which create little micro surges of their own that accumulates the surge, and since the energy has nowhere to go, all it can do is build up. Now, there's one fundamental leveraging agent to this circuit to allow the surge to develop in the first place, and that is the quote that William Line ascribes to Tesla, but we can't find it elsewhere. William Line is the only source for this quote, and he says that Tesla says that for every 200 pounds of iron added to this device, 1 horsepower output is increased. Now, it's a big enigma. How do you add the iron to get that kind of result? And that does not imply a surge either. It could be anything. It could be a surge, or it could be just more output that's at a level, constant rate. In Paul Falstad's simulator, which is my favorite simulator, surges are easy as pie. And there's a couple of reasons for that. Sorry, I'm losing my voice. There, maybe I got it for a few more minutes. There's a couple of reasons. First of all, he never put resistance in his coils. His coils operate as if they're operating at 0 degrees Kelvin, which is not realistic for the common person monkeying around in their garage. We don't have access to special metals. We don't have access to liquid nitrogen or helium. So we got to deal with resistance on the coil. Not only inductive resistance, but just the resistance due to the length of wire that's there. Paul Falstad also does not put resistance on his wires, and he puts no resistance on his junctions. So I was able to add equivalent series resistance to his coils and his caps. I was unsuccessful at modifying his Java software code to add resistance to joints and wire. So what I've done here is I've added resistors. They're either 300 microohms or 100 microohms. The 300 represents a junction, or a junction between two sides, a two-sided junction. So it's got a junction on one side and a junction on the other. The 100 micro shares a three-way junction, so I have it divided up. Let's see what else. So what I've done, even though you see wire here connecting various components, and the wire seems very long, stretched all over the place, that's just to make the circuit easy to look at. It doesn't mean you shape it this way. There's two rules of thumb that Eric Dollard and John Bedini kept repeating all the time, and that is never use clip leads, always solder, and if you have to have wire connections, keep them as short as possible. And also pay attention to the wire gauge that you use, that it does not offer any resistance regardless of its length, because you're dealing with microsurges when they first appear, and they can easily be suppressed if there's even the slightest resistance in the circuit. Now, this version you see before you is today's version. Prior to this, I never had all of these 100 and 300 microohm resistances representing solder joints, and so the circuit behaved a lot differently. It was easier to create a surge. It was a little too easy. By putting in these resistances, it's a little more difficult, which is good because it helps buffer. It helps buffer the tendency for a surge to develop. I'm really good at developing surges. I'm too good at it. The hard part is managing them. That's always been my challenge. After the initial few months of getting used to surge-oriented circuitry, it takes a while, to think in a new way. But after, it doesn't take long before it becomes so easy. Even in LT-Spice, it's very easy. Microcap, it's not easy because microcap suppresses surges, and so you never even get to see, unless you really look for it, that the surge actually developed because it is suppressed so quickly. But you can. If you scale down the time frame, you will be able to find the surge that, for a very short period of time, it had a little lifespan. LT-Spice makes it difficult to create a surge, in as much as the advice they give you online for how to deal with a certain error message is the wrong advice. It's the right advice for getting rid of surges, but it's the wrong advice for encouraging them. And so I figured out how to get around that, and when I did, it made the surge worse, in the sense that it was harder to manage. It made it easier for it to be extreme, an extreme surge, and we don't want that. We want a regulatable surge that gives us free energy, which is not that easy to produce. So in this circuit, it's not bad. It works pretty good because we don't use capacitance to develop the surge. The capacitors are here, but it's mainly the magnetic force of this circuit which creates the surge, and that's really good because magnetism is very poor at creating a surge. Capacitance is far superior, in my opinion, and I've done a lot of hours of this. So if you really want to explode something, use capacitors to instigate the surge. But if you want something manageable, try to keep the capacitors there only in a supportive role and not in an active role. Also, diodes can exacerbate a surge, but these diodes do not do that because I engage them only in drainage mode, not in surge mode, in order to run the batteries, to charge them. What I do need to do is I need to toggle back and forth between the use of an inductor to induce the surge, and then I toggle out of the inductor and over to the batteries when I want to maintain the energy level rather than encourage it to surge. Now, oddly enough, this circuit surges anyway. it just doesn't surge very quickly. It takes a much longer time to very slowly increase its overall energy value when you're so-called out of the surge mode. In other words, normally when I use capacitors to create a surge, when I come out of the surge mode going into drainage mode, and drainage mode is pretty much the only mode that most of us are familiar with, it usually is a very big digression, and so you really see the drainage happening because the third law of thermodynamics, or the second law, whichever one it is, really kicks in, and you see the energy level very quickly drop. In this circuit, it never drops. It just keeps escalating. It's just so slow you don't see it unless you run this circuit for several hours in real time, although it doesn't amount to much in simulator time. And then you start to see that it's gradually increasing itself. It's just not a whole lot like it was before. So from a cold start, you want it to surge to develop an energy level, because by and large, what I do to create over unity without having to worry about how I measure anything, very simple. Don't give it much of anything to start with, and then cut off your source, your external source that's driving the circuit, and now it has to run on its own power and build it up. And so you don't have to worry about measuring anything, because anything you see is going to be a gain. It's a very easy way to measure an over unity circuit, let me tell you. But this works in the simulator environment, and a simulator environment is part reality, part make-believe. So take these simulations with several grains of salt, not just one. But I do try to increase reality, and so adding the solder joints helps a lot. And adding equivalent series resistance to caps and coils helps considerably. Anyway, be that as it may. So what I did was I patterned this circuit off of the needs of my electric car. My electric car has dead batteries at the moment. I can't drive it. It's a RAV4 EV from 2002. And the amperage delivered to the batteries by the magnet charger, the paddle inductive charger, when the car is recharging its battery pack. And by the way, it's a double-sized battery pack, 288 volts, 24 modules of 12 volts each, 95 amp hours each module. Well, each battery, it's made up of actually several modules inside each battery, 24 batteries. Takes 5 to 6 hours to recharge, and it runs 2 AC motors, and that's why the pack had to be doubled. And to recharge it, it requires 240 volts. The amperage, I think, is 20, I want to say 26 or 27. I think it's 27 minimum amperage that has to be delivered to the magnet charger at the AC wall outlet. Anywho, when the magnet charger converts that, it delivers 20 amps to the battery pack. They're all wired in series. So in this circuit, I've divided them up into 4 quadrants, or 4 divisions, because of the oscillatory nature of this circuit. And then I put a diode on each battery to make sure it gets charged and does not allow it to be drained to any significant amount. I mean, it does drain a little picoamps, but it's mostly amperage, in this case 15.5 amps negative, that's being forced into the battery, the 72 volt battery quadrant. And then I put 36 milliohms of resistance on each battery, because the other thing I could not change in Paul Falstad's software code is resistance on his batteries. He had none, and so I have to put a resistor out front, and I put it out front the nose, or positive terminal of the battery, and I picked a value based on my nickel metal hydride batteries in my car. They tend to be somewhere around 6 milliohms of resistance when they're healthy. So that works out for a 12 volt battery. That's half a milliohm per volt, and so I just linearly factor up. So for 72 volts, that amounts to 36 milliohms of resistance. So that's another reality check I had to put in here. The value of these 4 capacitors of 10 microfarads is arbitrary. It doesn't matter what they are, because they play a supportive role. They do not actively regulate the circuit, but they do help play a supportive role, I found, putting them in. So I put them in, but it doesn't matter what value they are. So they can be anything you want them to be. They just have to handle high voltage, like everything else in this circuit has to be able to handle high voltage. Also, these 1 Henry coils are dummy coils. They could be the motor coils, or they could be just dummy coils, and they're there to surge the circuit. Once it surges, then we flip over to drainage mode, which is what this picture, this screenshot is showing you at the moment, and then the batteries get charged. Now there are three things you have to do to switch back and forth between the two modes. In order to go into battery charging mode and step out of surging, you have to open this switch here that disconnects the clock mechanism from toggling these four switches back and forth. Because these toggles create surges, and the surges feed the circuit. Without the toggling going on, there's no microsurges feeding the circuit, and the thing won't build up. Now it's alternating between two transformers, so it's got these two inductors that are constantly being utilized. The batteries are cut off by these manual switches, and it toggles back and forth between two transformers. And this is a very interesting situation about Tesla's special generator. He has two sets of coils, his M coils and his double H coils. So he has actually 4 H coils and 2 M coils. The M coils, each one is on a horseshoe core, and the horseshoe core is huge and heavy and massive. And the M coils are thin wire, 50 to 100 miles long each M coil, according to William Line. So many turns of very thin wire. And so you can expect the M coils will build up a lot of voltage and are not intended to run at a high current. The H coils, on the other hand, are very teeny-weeny coils on a very narrow core, the material of which I don't know what it is, and the core is a rod. And I believe they're a single layer winding. And so their inductance value, their self-inductance value, is going to be very small by comparison to the M coils. Self-inductance is going to be very large. The mutual inductance of the M coils are probably standard for any transformers. So in this simulation, I use 0.999, 99.9% coupling coefficient. And then on the H coils, I use the same, although because they're a single winding on a tiny core, it's probably going to be less than 0.999. But I tried other values, and I didn't get any different results, so I just used 0.999 for the purposes of the simulation. And it doesn't seem to change any of the outcome. What does change is the coupling coefficient of the H coils. And that's what makes Tesla's special generator so special. We don't consider coupling coefficients to be a source of current. Yet if you go into Paul Falstad's simulator Java software code and look at the calculations for current for a transformer, you will find that the coupling coefficient will alter the current, the outcome of the current calculation, for the calculation for current, based on what the coupling coefficient is. Now, most of the time it doesn't vary a whole lot, because we have this silly notion that it can't vary. It goes up to unity or just shy of unity and stops, and then it can go less than unity, and then becomes more difficult to make it too much less than unity, and then it kind of becomes harder and harder to make it too small. You know, air is going to have a certain coupling coefficient as opposed to ferromagnetizable iron. And then we get, we get a certain amount of latitude, but that's generally considered that's it. Well, lo and behold, there's a way to get around that. And what you do is you do experiments on magnetism. I learned this from lessemf.com, and they sell various barriers for electrostatic sensitive individuals who want to shield themselves from electrostatic fields. But they give you the caveat, when it comes to electromagnetic fields, you cannot shield yourself. It's impossible. All you can do is reshape the magnetic field that you're trying to deal with. You cannot block it. There's no way. It'll pass right, it'll be absorbed by the magnetic material or whatever material you're trying to use, and then be re-emitted on the exterior side. Now all you can do is reshape it, and I learned that also once I learned that on lessemf.com, I went to YouTube and I found these ferrofluid videos on YouTube, and they have a oversized flathead screw sitting on its head in a pan of ferrofluid, and underneath the pan, let's say is glass. Underneath the glass pan is a strong electromagnet positioned right under the head of that very large, massive flathead screw. And as it increases its power level of the electromagnet, you see the ferrofluid slowly move up the shaft of the screw towards the tip. And then it moves along the edges of the screw, not in the valleys, the smooth valleys. No, it avoids them. And it congregates at the tip, the pointy tip. A big, huge glob of ferrofluid is hanging there, defying gravity, pointing, sitting on the top of this pointy tip of this screw. And that teaches that the magnetism wants to emit out of a magnetizable material at the edges, not along the smooth surfaces. So when we wind a wire around a ferromagnetizable core shaped in the shape of, let's say, a cylinder, we're doing it all wrong because we're putting it in the wrong place. All the magnetism is shooting out the two ends of that tubular. Let's say it's a pipe, a galvanized steel pipe you choose to use to wind your winding around. It's going to be shooting out the two ends of the pipe, bypassing the coil altogether. Instead of coming out the sides, which we are expecting it'll do, it won't. So we're sending magnetism into the magnetizable core from the coil, but it's not coming back out to the coil. And maybe that's the way we want it. I don't know. I'm not an electrical engineer. We want it to be one way. Regardless, when you're dealing with a transformer, you do want it to come back out again at the secondary coil. The primary is supposedly sending it in, the secondary is catching it on the way out, and the secondary is in the wrong place. Now, Tesla had a habit sometimes of putting grooves in his generators, so I imagine if you're building a transformer, it wouldn't be a bad idea to put striations where you plan on putting your coils, and then lay your coils on top of the edges of the striation, not on the valleys. Anywho, so that's what I learned about and then I did an experiment. I wrapped a piece of iron wire around a plastic pipe in which I had placed 9 neodymium magnets, ring-shaped, and the middle 3 were flipped around, and the pipe was just narrow enough to prevent them from flipping somewhat, and to encourage or to discourage flipping even further, I put a bamboo skewer through the center of the 9 so that the middle 3 would not flip back. And so I had 2 opposing sets of poles, 2 norths and 2 souths, because of the middle being flipped around. And then I put end caps, glued them shut, and I put mu metal around the center of the pipe in the vicinity of the 2 double poles. And then I soldered. I used liquid solder to connect and wrap the iron wire to the outside of the mu metal. And then I wrapped the whole thing in bubble wrap, and I had the iron wire was a long stretch. It was 10 feet long. Then I had my ex-girlfriend hold the pipe magnet end, and I held the other end of the 10-foot wire, and I held a compass up to the wire, and there was a magnetic field at the wire. And so that taught me that I was succeeded in reshaping the magnetic field of those magnets to extend it all along that 10-foot strand, single open path strand of iron wire. Just regular galvanized wire you get from the hardware store. So that was a very important set of experiments and things for me to learn about magnetism. Well, it's very important. It's very applicable. It's very relevant to this Tesla special generator, because what I believe he did was he magnetically coupled the core of certain coils, not all of them, to a much larger iron mass. And it has nothing to do with mechanical vibration, it has nothing to do with dissipation of heat, it has nothing to do with being an electrostatic sink. Not that all those 3 are involved, but they're not the reason for doing this. The reason is to diffuse the magnetic charge in the core of the H coils. Diffuse them. Diffuse that magnetism. Why? Because if you have a density of energy, in this case, magnetic dipoles in an iron core of a coil, you get a lot of conflict because they're radiating magnetism towards each other, creating cross interference. And when you get it It's just like people, when you pack them together in a bus or a train. No, excuse me. The best example, vegans love to point this out. Factory farming, when you shove a bunch of pigs in a very tight area, it doesn't take long before they start to bite and attack each other and literally injure each other in a major way. They get very violent against each other, biting out chunks of flesh, really huge chunks, and disabling certain pigs, in a very drastic way. And you lose your pigs that way, just because you pack them together. And that's why free-range chickens are such a big deal, because you allow them to run around outside instead of caging them in a very tight area where they're all compressed like sardines, and they go nuts because that's not their normal. They're not fish. They're not sardines. A school of fish. No, birds like to, and other animals, especially mammals, mammalian animals, they like to spread out like us. Live in the country, have a lot of distance between your neighbor and yourself. It helps. It's more congenial. It's less stressful. Well, it's the same way with magnetic dipoles. You get them packed together really dense in a highly saturated state in a core of some coil, you start getting cross interference, which causes decay over time, and whatever you lose over time, you lose. You have to replenish. But when you have it in a state of diffusion, in a large iron mass of several tons, it's all yours. You own it. You didn't lose it. It's there. It's just diffuse. But it won't decay. And anything you add after your initial add, every time you add, it just accumulates. And it becomes a reservoir that keeps getting bigger and bigger. And this is what the coupling coefficient represents, I believe. Okay? This is speculation according to Vinny, or guessed estimate. This is my best guessed estimate, that the coupling coefficient represents the mass quantity of the ferromagnetizable substance in the core of a radio choke coil or a transformer situation. And we just have to think out of the box to start thinking that we can get that coupling coefficient above unity. Now, I can't tell you how much, because I don't know, how much mass of iron equates to the coupling coefficient. I would suspect it's logarithmic, but I don't, so that only makes it harder to speculate what the relationship is. But we have no data. See, there's no data for me to go on, and I certainly don't have any data, so I'm not going to speculate. I just know that I have to get this coupling coefficient up in the range of, I believe it's billion. And actually, in Java software, there's a limit for double. Certain kinds of integers are called double. They're not integers. They're decimal numbers with a certain number of digits available that you can utilize. And I believe 2 billion or 10 place values is the limit. So I'm limited to 2 billion. And I find that with these solder joints, my minimum has grown from 1 million to 100 million, on up to, I use the max of 2 billion. It's a certain value, 2 billion and something something. I just, rounded to the nearest bunch of zeros. It's easier for me to remember. At the age of 61, your memory goes, so I try to keep it simple for myself. So when I'm in surge mode, I change the coupling coefficient of the H coils on this bottom transformer to be 2 billion. And I close the switch, and I toggle the switch to disconnect the batteries and connect these 1 Henry coils. There's one on either side here. And I run it, and it's at a 300 microsecond time step, and the clock is now at 500 cycles per second. I had to raise it. I had it previously at 100, and in Tesla's special generator, he has it at 80, according to Thomas Comerford Martin, which you can go find at archive.org using this shortcut is.gd. That's independent Samuel George David /specgen pgis. So that would be SPECGEN PGS. And I've transcribed chapter 63 of Thomas Comerford Martin's book, all of which, the whole book, deals with Tesla's inventions, but that last chapter deals with a demonstration that Tesla performed for a small group of electrical engineers, including Thomas Comerford Martin, in the year 1894 at one of the World's Fairs. I didn't know where it was. I can't remember where it was located. Let's say it was Chicago. I don't know. And the following year, Tesla had his fire, his lab fire. Everything was destroyed. And one of the inventions that went with his special generator was his invention of the liquefaction of air. And immediately upon the fire, the lab fire in 1895, Carl Linde of Germany, Linde, patented the exact same invention that Tesla had been working on. So it's obvious the Germans had been stealing from Tesla or had been given outright Tesla's inventions for about half a century, beginning in 1895 and ending with Tesla's death in 1943. He was, according to William Line, he's met with Werner von Braun in New Mexico for 2 years, between the years of 1936 and 1938, gave Werner von Braun outright his special generator, along with his UFO technology and the neutron bomb, several different technologies, because, our government thought Tesla was a kook, a crackpot, didn't pay him any attention, and then the Germans, even before the Nazis, paid attention, and that's why that was the predicate of their war machine, of World War II. I can't say anything about World War I, but World War II was predicated on Tesla technology. They also had other technologies they had figured out on their own, like how to turn coal into gasolines, because they don't have gasoline, but they have coal, and so they were able to create their own gasoline fuel for all of their tanks and whatnot from their coal deposits within the boundaries of the German land. The Nazis did not lose the war. They lost their country and all the countries they had taken over. They did not lose the war. They simply lost the land they had taken over, and they've been the superpower, a priori superpower ever since. But they never get the credit. Instead, we play this game between the Americans and the Russians, and now it's the Americans and the Chinese, or the Americans and the Koreans, or the Americans and Iraq, or the Americans and the terrorists, or the Americans and the aliens. It's always somebody other than who really is at the top of the pyramid on this planet Earth. They like to remain hidden. That was part of the deal, is to go into hiding, and they've been in hiding ever since, but their technology has only gotten more sophisticated since then, and 9/11 has everything to do with Nazi technology. Whether you want to agree with me or not, that's my opinion. And the opinion of a few other people. So this is Tesla's special generator, and it's a crude version. There's also his trimetal generator, which is a derivative, which includes the use of aluminum. And I include it here in the sense that I include capacitors playing in a supportive role, because ceramic capacitors, one of the most popular capacitors in use today, the dielectric material is not just ceramic. That's the matrix within which the active ingredient is embedded, being aluminum oxide. And so aluminum is in our capacitors for the most part. So we've already got a trimetal generator going on here in a sense, provided we use the fundamental premise, 200 pounds of iron, 1 horsepower is increased. That's the premise. Everything else is extra window dressing. So the trimetal generator is a derivative, I believe, of his special generator, but there's also a solid state version, and that is a mystery to me, and I do not know what it is. Possibly, what has come to my attention recently is Thomas Bearden's MEG, the MEG. I had heard about it some years ago, but now I'm a little smarter, and I think it is the solid-state version of Tesla's special generator. But like any good patent attorney, he advised Thomas Bearden to leave the a priori secret of that generator out of the patent, and what has been left out, to everybody's common knowledge, is that quote that William Line got from some source or another. William Line didn't get it from Thomas Comerford Martin because he didn't get it from Tesla. William Line has contacts in Defense Department and CIA, top-level clearance, family members and whatnot. And even the CIA wanted to hire William Line, and he's refused. So he's had these contacts that and friends, acquaintances, family members. They give him various pieces of information, and plus he's been on the inside of certain things like the Cuban Missile Crisis. He was there. He knew exactly what was going on. Anyway, if it wasn't for William Lyon being interviewed by Bobby Kennedy, John Kennedy would never have gotten the correct information to act upon, because the CIA was feeding John Kennedy false information to encourage the Cuban Missile Crisis and to encourage a thermonuclear confrontation with Russia, with Khrushchev. And that was avoided because William Lyon gave Bobby Kennedy the correct information. So William Lyon has had this fortuitous good karma, you know, that's an oxymoron, right? A double positive. Of finding out stuff that other people don't find out, and this is one of them, that quote, 200 pounds of iron, 1 horsepower is increased. And we have to go on that, because it might be what's missing in the Meg that makes the Meg so special, because people, Nowden, J.L. Nowden, he is probably the best person to say that, or one of the most well-known to have experimented with replicating Thomas Bearden's MEG, his solid-state magnetic generator, a magnetic-oriented generator. But he doesn't include that because there's no indication to do so. And I suspect, looking at it, it looks just like Tesla's special generator, except that one intrinsic active ingredient is missing of the extra ferromagnetizable mass in a very large way, in a very large quantity. So enough of the preparatory conversation. The whole point of this video is to show you how to operate these softwares so that you get the results that you're looking for. So when you first open it up, this is what it looks like. You turn it on, and then you flip the switch, the toggle switch, over to the batteries and back to the 1 Henry coil, and now everything's gotten a small charge so that it can begin to surge. And you'll see the surge happening way down here. Here's the spike from transferring the charge, but now the surge is beginning. And it proceeds along at a nice pace. And it's going to overtake the spike and cause the oscilloscope to shrink the spike in perspective as the surge continues to grow, both in the positive and negative direction, and alternate fashions. Despite the flipping and toggling, governed by this clock timer, there's other oscillations going on in the circuit in its various modalities that are self-managed in a very random, haphazard manner. And I don't try to control them. If we stop this momentarily and go back to the image, you see a band of color here. And it has an upper, the amperage has an upper maximum of 5.44 picoamps, and the negative is negative 15.44 amps. What this is basically is a squished, squashed, compressed AC wave that has been shifted downward in the negative direction so that most of it is below the baseline of the oscilloscope tracing and very little is above in the positive side of the baseline. For the voltage alongside it, we have, in this case, we have 454 femtovolts positive, and we have 555 negative millivolts. So again, it's a squashed AC wave that is so squashed that we don't get to see the wave. It's basically either a squashed wave or a square wave. I believe it's a squashed sine wave. I suspect it's a squashed sine wave, compressed in time. It's a time compression, so that you get this band of color and you don't get to see the behavior of the wave itself. But that's basically what this band of color is indicating. It's a squashed, oscillating wave, probably AC, that's highly time compressed. So, that's the kind of thing going on here. And then we don't know the periodicity of that wave. It's probably not even a regular periodicity. It's probably varying frequency or, wavelength in terms of time. In terms of the phase relation of when the wave occurs, up and down. Well, yeah, the wavelength, right. Now, one of the things that Thomas Comerford Martin liked to point out in Tesla's special generator during the demonstration of 1894 was that Tesla was trying to achieve a precise regularity of periodicity. This was very important for him for one reason or another, and I don't try to go for that at all. That's why I say, take this simulation loosely. It's about as close as I can come based on the fact that I don't have the wherewithal. I'm limited in this simulator as to what I can do or cannot do. I cannot take the coupling coefficient any higher than 2 billion because that's as far as a double, I forget what double means, double digit? It's not an integer, it's a decimal. It's a decimal value. Anyway, because if you go any higher, you have to use floating point, and I don't want to do that. I'm trying to stay as accurate as possible, and that limits how much absolute magnitude how far I can go with absolute magnitude of the values in the circuit. So now we're up to femtovolts, and it's for this resistor here that we're looking at down in here to know when to turn off the surge. We're up to femto, and my target is to be around 60 volts, 60 microvolts on this resistor, and right now it's at 244 femtovolts. Oh, now the negative is 1.2 negative picovolts, negative 3 picovolts. Now it's going up positive 3, positive 8 picovolts. So we're slowly edging our way towards 60 microvolts is somewhat the target, and then we'll achieve somewhat the goal. It's not going to be precise. That's one of the other problems about my simulations of surges is that the lack of precision. It's all I can do is get within a certain window of approximation, and that's the best usually I am able to do most of the time. Sometimes I exceed that and actually get precise outputs, but under those circumstances, it's usually because the circuit simulation is not accurate to reality. There's a certain amount of non-reality going on, a certain amount of make-believe, in which I can achieve that kind of accuracy. Because when I put realism into the circuit, more and more realism, I lose control little by little. And the circuit becomes a little unstable, too. Oh no, we're still in nano. My fuzzy eyesight made it look like milli. Maybe if I squint. Oh, there we go. So we're up to 2 micros, so we're looking for 60 micros, either positive or negative, one or the other. Now if I squint my eyes, that does help a little bit. And get closer to the screen. We're up to 10, 20, 30, 45, 60, there we go. Negative 63 and a half. So now we toggle over, so this was engaging the 2 1 Henry coils. It was not engaging the batteries. Now we toggle the manual toggle switches. These are the automated analog toggle switches, but right alongside it is the manual. They can go back and forth, see? They all go together at the same time, and now I've disengaged this component, this inductor, which helps the surge occur, to the batteries. And so now I'm not going to be encouraging a surge anymore. I also open the clock switch, so now the clock is disengaged, so the automated switches will be frozen in one position only. The position being, they will disconnect this transformer and only engage the HH coils. Then we go into the HH coils and we change the 2 billion figure to be 0.999. Now, the inductance on this transformer that we've disengaged from is 1 kilohenry. That's something I forgot to mention. It does need to be mildly large, in contradistinction to the 1 picohenry self-induction of these HH coils. Okay, so now we re-engage the simulator, and we see that the voltage shoots up to 2 millivolts, positive and negative, on that resistor. And the amperage on the batteries is a little higher than what I wanted, 7.78 amps. But very little voltage. Very little voltage on the resistor on one side, and on the resistor on the other side. Let's find out what that is, how much voltage. looks like 227 femtovolts negative and 2.33 millivolts positive. And this was 280 millivolts negative. So we've got 280 volts, 280 millivolts negative is the highest voltage level alongside this battery. Normally, you have to, in order to charge a battery, you have to have voltage slightly greater than its rating, which in this case is 72 volts. And yet here I'm getting away with using millivolts, less than 300 millivolts to charge the battery, a 72 volt battery group with almost 8 amps of current. I mean, that's not bad, you know. Talk about not overheating the battery, not straining it with too much voltage, you know, over voltage. And I'm keeping the amps low because I don't want to strain the battery in that sense, you know, burn it up and age it rapidly. And so at the rate of 8 amps, it should have been 5. You know, all of these 72 volt battery groups, all 4 of them, when you add them up, they're 288 volts. They would have required 20 amps at 360 volts to charge them in 5 to 6 hours. Now, they're not getting 360 volts. Okay. No big loss, I guess. They're getting 300 millivolts instead, but their amperage is nearly 8 amps for each quadrant, which means times 4, that would be 32. So they're getting 32 amps instead of 20, so that's a little more than 50% more than 20, which means, well, let's do them. I hate doing things in my head. Let's see, 32 divided by 20 is 1.6 times, let's say an average of 5.5 hours. Oh no, you'd have to do it the other way. Oopsie. No, wait a minute. 20 divided by 32 times 5.5 hours. So in 3.5 hours, this will charge the battery pack. So it's not level 3 charging, you know, like supercharging, and it's not level 2 charging. It's somewhere in between the two. And I chose this because I chose battery charging for this circuit because then I didn't have to worry about waveforms. You know, a motor is a bit more picky, more finicky about what kind of waveform you feed it, especially a AC motor. Batteries a little more forgiving. But we do have to keep in mind that batteries are not designed, the chemistry of a battery, it is not fortuitous because of the chemistry of batteries in general to both charge and discharge at the same time. We get away with lithium batteries to do that, but if you've ever noticed, lithium batteries tend to overheat. Gee, duh, because we're doing 2 opposite chemistries at the same time. The electronics, the electrical transfer of energy during charge versus discharge is conflicting, and it's never a good idea to do both charge and discharge at the same time, regardless of what kind of battery you're using, lithium or otherwise. Your cell phone is cooler if all you do is charge it with the cell phone off, and you use the battery without discharging it with the cell phone on, and that keeps the lithium battery as cool as you can get it to be. If you want to heat it up as much as possible, then run all your apps at the same time and charge your cell phone at the same time, and you'll get a nice hot cell phone, which ages your lithium battery and causes it to lose its capacity to store a charge prematurely. And then you got to go buy more batteries, not just recharge them. You got to buy new ones. So it abuses, basically. We're abusing our lithium batteries because we want to charge and discharge at the same time, which is not good. So I set up this circuit simulation on the presumption that we're not trying to do that. All we're trying to do is charge the car overnight, or when you park it. So let's say you go to work and you park it, and you don't have to plug it in to the grid to charge it. You just use a little bit of energy from the battery pack that's still there to charge up the circuit, to give it a very minuscule, trivial charge, and then you disconnect that when you're building the surge. So the batteries are not contributing to the buildup of the surge at all. It's merely the mass of iron in the chassis of the car, if it has any iron to make use of. It won't be, tons. It'll just be, several hundred pounds, maybe 1,000 if you're lucky. Nowadays, the cars are so lightweight. My car, on the other hand, if you take away the battery pack, the weight of a RAV4 from 2002, which is all they did, Toyota just converted a RAV4. They didn't bother to redesign it. So it's not like their Prius, is redesigned from the ground up. But their RAV4, it was an experimental production run. It was a test run. It was not a full-scale production run. They only made about 14 to 1,600 of them between the years of 1998 and 2003. Without the 1,100-pound battery pack, the car weighs in a little over 2,000 pounds. And then if you take away the glass and the rubber and plastic and any unfortunate lack of connections between iron parts such that you lose magnetic coupling among those magnetizable parts, and assuming that iron is magnetizable as well, we're talking maybe less than 2,000 pounds to some degree that we get to work with. Now, it's no mistake or it's no accident that Tesla chose a Pierce Arrow in 1931, because a Pierce Arrow is a very heavy car. It has no battery pack. He did not use one. And the Pierce Arrow weighs in at over 4,000 pounds. That's a lot of mass of potential magnetizable iron to make use of. And I suspect he used a derivative of the special generator that he showed Thomas Comerford Martin in 1894. He used a derivative of that in 1931 that he was able to scale down into the size of his project box, which was 2 feet long and 1 foot square rectangular box, his project box. And 12 vacuum tubes and some wire. You can make a transformer out of wire. You don't have to use laminate core. In fact, Tesla has a patented transformer in which he used iron wire as his magnetizable mass in between his secondary layer of copper winding and his primary layer of copper winding. So there are different ways, and that is a kind of a substitute for a laminate core. So, there are different ways of doing things. You don't have to do it always the same way. But somehow he managed to get enough power to power a significant horsepower AC motor to drive a 4,000-pound car around at 90 miles per hour for a week, and no battery pack. And he was not receiving energy from the environment or from some broadcast station. The antenna was on the car to dissipate electrostatic charge. And the FCC came into existence 3 years after his demonstration in Buffalo, New York, to put a stop to such things. They don't want people to build up an electrostatic charge. There are ways of preventing that from building up by blowing compressed air across a pair of plates that you allow to charge up, and then you ionize those plates rather than allow them to broadcast electrostatic interference into your environment. As for electromagnetic interference, that's a whole other story. The chassis would have absorbed that, but we'd still have the electrostatic interference to deal with, and I think that's what the Ariel was trying to dissipate by way of conversion into ions, ionically charged air molecules that would then ground out to the nearest object they came up against. Whether it's positive ions or negative ions or a mixture, I don't know. Certainly negative would be healthier and would clear the air of smog and smoke and fog. And the other weird oddity is that immediately after the demonstration in 1931, Pierce Arrow went out of business. They were dependent on another company to manufacture the transmission for the Pierce Arrow. They did not make the transmission themselves. And when that other company went out of business, that put Pierce Arrow out of business because they couldn't find somebody else to make the transmission, I guess. So another one of Tesla's attempts to become commercially viable went belly up, unfortunately. Oh, what's this? We have some amperage on this resistor. Yeah, 8 amps, that's right. So, that concludes... Oh, I see. Whatever. We don't need that scope. So that concludes this demonstration. Now, if you wanted to reset this and start over, you're not going to get exactly the same results. Only when you get a fresh instance under improvements, improvements, new and revised components, transformer, adding coil, core mass for growth. Only when you start from a fresh instance are you going to get exactly, well, not exactly, but more or less the closest to this consistent results. But if you start it and use it like I was just doing, and then hit the reset button to clear it, stop and then hit the reset button, and then change back into surge mode, you're not going to get the same results. It'll be slightly different. So this is the problem of simulating something that I don't fully understand. Surges, how does it? Nobody understands them because nobody studies them. Steinmetz studied them. He had to. He was hired to suppress them, and that's what he did. Among other things he was hired to do, like break the Tesla patents on the AC motor and generator. Nobody knew how to build an AC motor or generator because Tesla didn't tell anyone. He had it locked up in a patent. Westinghouse was getting all the benefit. And so Steinmetz was hired by General Electric, I believe it, or Westinghouse. No, Westinghouse was the one that had the patent. No, I think it was General Electric. Well, anyway, whoever hired Steinmetz to break the patent, he succeeded. And then people could build AC, competing companies could build AC motors and AC generators, and they would work instead of fry themselves, because that's what they were doing. They would suffer ultimate meltdown instead of being able to function, because nobody could understand how they were supposed to be built, and Tesla didn't tell anyone. The privilege of an invention. So that's why I suspect the MEG, Thomas Bearden's MEG, does not give us everything we need to know to make it run the way it's supposed to. And I suspect it's a revival or a reincarnation, if you will, of Tesla's special generator, the solid state version. But that's my hunch, based on what I see and what I know now about Tesla's special generator, because I've spent a good deal of time. 4 years I committed myself to try to figure out Tesla's special generator, and it's been very slow going until towards the end it's been speeding up. All of the little inspirations and insights has been accelerating the progress. So I think I've said enough. I'm going to post this on Vimeo, and now you'll know how to run this circuit in the background to it and yada yada. Now I just have to close off the video.